In this video, I'm going to go over the hydroboration oxidation reaction of the terminal alkyne, which will convert this terminal alkyne into the aldehyde here. So we know that this molecule has a terminal alkyne because the alkyne is at the end of the chain, since we have a hydrogen attached to it. So whenever you're given these two reagents here, R2BH, in this case, our R group is Cia, and the second step, H2O2, the peroxide, and NaOH, this is an indicator of hydroboration oxidation. So whenever you have H2O2 or R2O2, which is a peroxide, you know that this is going to be an anti-Markovnikov reaction. So let's go over the mechanism of this reaction. The first step of this reaction is hydroboration, where the R group Cia is this over here. This is the boron, this is the hydrogen. Since this is an anti-Markovnikov reaction, the less substituted side of the alkyne, which is this carbon here, will attack the boron, and the boron will be attacked because think of a boron as an electrophile having a positive charge since it has an empty p orbital. So since it has an empty p orbital, the nucleophilic alkyne, the less substituted side of it, will attack the boron, and this bond between boron and hydrogen will break, and the hydrogen will attack the other side, the more substituted side of the alkyne, giving us this intermediate here, where the hydrogen is now attached to the more substituted side, and this Br2 group is attached to the less substituted side of the alkyne, and now the alkyne turned into a double bond. That's the first step of the mechanism. Now let's go over the second step of the mechanism, which is oxidation, where we now bring in our H2O2 peroxide and NaOH base, which we do an acid-base reaction here. We deprotonate the peroxide, form our hydroperoxide ion here, and now boron still has 3 bonds, which has an empty p orbital. It's missing 2 electrons, which means that this hydroperoxide ion will attack that boron, giving this boron a negative charge with 4 bonds. So now this is where the weird step happens. This is the migration step. Boron wants to get rid of that negative charge. So this R group here will migrate and bond to this oxygen here and kick out the OH group. So the way that I keep count of what groups are attached to which groups is that I label the atoms that are moving and nearby each other. So I'm going to label this oxygen 1, this boron 2, and this carbon 3. So since that this whole group is going to migrate to that oxygen, this carbon 3 is going to break the bond between 2. So the bond between atoms 2 and 3 will break, and we will form a bond between atoms 1 and 3, which we see in this case. This intermediate here has the new bond between 1 and 3, and the bond between 2 and 3 broke when we migrated this whole group to this O group and kicked out the OH group here. Now, this boron is now neutral, but it still has 3 bonds and an empty p orbital, which we could use this OH group that left and attack that boron there, giving this boron a negative charge once again with 4 bonds. And now boron wants to get rid of that negative charge. So this OR group here will just leave by itself, giving this oxygen a negative charge here. And then the side product with the boron neutral. And then now we protonate this negatively charged oxygen with a water molecule here. And after we protonated it, we have an enol here. And after we have the enol, we do keto-enol tautomerization in basic conditions since we're given NaOH as the starting material. So we bring in another NaOH, deprotonate the alcohol, which we have a negatively charged oxygen here. We reform the carbonyl, and this carbon of the alkene will get protonated by a water molecule, giving us our final product here, which is the aldehyde.